Here we claim that the topological product n copies of R with the usual topology coincides with Rn with the usual topology on it. Here this Rn is the Euclidean space with the usual metric or Euclidean metric, and as we already know, this is a metric space, and hence the topology induced by that metric, that is the usual topology, makes it into a topological space. So we have the topological space Rn with the usual topology defined on it. As we have seen earlier in the previous session, we can consider the Cartesian product of R taking n copies of R, and we can define a product topology on this Cartesian product, that is on the set Rn, using the topologies on these coordinate spaces. We can consider the usual topology defined on each of these spaces R, and we know how to construct product topology on the Cartesian product of n spaces. So we have two topologies on Rn. One is the usual topology defined on Rn, that is the topology induced by usual metric on Rn, and another is the product topology, which can be constructed using the usual topology on each of these spaces R, and we claim that these two topologies in fact coincides with each other. That is, the usual topology on Rn coincides with the product topology on Rn. For the proof, let us denote by U the usual topology on R. Let τ1 be the product topology on Rn, while τ2 denotes the usual topology on it. That is the topology induced by the Euclidean metric or usual metric on Rn. We have to show that τ1 is equal to τ2. For convenience, we denote a point x1, x2, etc. xn of the set Rn by x bar and so on. So we can assume that d of x bar y bar denote the Euclidean distance, that is d of x bar y bar is equal to square root of sigma I varying from 1 to n xi minus yi whole square as the distance between the 2 points x bar and y bar. This is according to the usual metric or Euclidean metric. Then our τ2 is the topology induced by this Euclidean metric, that is our D. We need to show that τ1 is equal to τ2. So we will need to prove that τ1 is a subset of τ2 and τ2 is a subset of τ1. First we claim that τ2 is a subset of τ1. We need to show that τ2 is a subset of τ1. Since τ2 is the topology induced by a metric, or we can say that τ2 is a metric topology. So its base can be taken as a collection of all open balls. Hence, to show that this τ2 is a subset of τ1, it is enough to show that this base is contained in τ1. So, we need only show that every open ball with respect to this τ2 belongs to τ1. So, we will be considering an arbitrary open ball with respect to τ2. and we will show that this open ball is a member of tau1. Then we can conclude that tau2 is a subset of tau1. Now let us consider an open ball, say B x bar r. This means this open ball is centered at x bar and its radius will be r. We will need to show that this open ball belongs to tau1. Remember that tau1 is the product topology defined on Rn. Now for any y bar, any point y bar of our open ball B x bar r, we are going to find some gy bar from tau1 such that y bar belongs to gy bar and gy bar is contained in bx bar r. That is, we are going to show that this bx bar r is a neighborhood of y bar with respect to tau1. Then we can conclude that bx bar r is equal to union of such open sets, and hence this set bx bar r is open with respect to tau1. So we will need to prove the existence of such an open set gy bar which satisfies this condition. So let us suppose that y bar is a member of the open ball bx bar r. Then the distance between these points dx bar y bar will be definitely less than r, and hence the difference r minus d of x bar y bar will be greater than 0. So we can choose an epsilon such that 0 less than epsilon less than r minus d of x bar y bar all divided by root of n. Also assume that for each I varying from 1 to n, Vi denotes the open interval in R of length 2 epsilon and centered at yi. That is, Vi denotes the open interval yi minus epsilon yi plus epsilon. Also, let gy bar be the set v1 cross v2 cross etc. cross vn. Then, since these sets v1, v2 etc. vn are all open sets in R, this is in fact an open box in Rn with respect to the product topology, and hence this set v1 cross v2 cross etc. cross vn, this set will belong to the product topology tau1. Now, since yi belongs to Vi for each I varying from 1 to n, and since gy bar is the set v1 cross v2 cross etc. cross vn, that is, y1 belongs to v1, y2 belongs to v2 and so on, yn belongs to vn. So we have the n-tuple y1, y2 etc. yn. This will belong to gy bar, that is y bar. This point is a member of the set gy bar, and we need to show that this is the required set. That is, this set will be contained in the open ball bx bar r. Now we are going to prove this inclusion. For that purpose, let us consider an arbitrary point from this set gy bar. Let z bar be a member of gy bar. Then we can see that d of x bar z bar is less than or equal to d of x bar y bar plus d of y bar z bar using triangle inequality, and we know that this sum is equal to d of x bar y bar plus d of y bar z bar can be replaced with square root of summation I varying from 1 to n yi minus zi whole square using the formula for Euclidean metric. But we know that vi, the open interval, is yi minus epsilon, yi plus epsilon, and gy bar is v1 cross v2 cross etc cross vn. So since this point z bar belongs to gy bar, we can say that each coordinate of the point z bar must belong to the set vi for each I varying from 1 to n. So zi belongs to the open interval yi minus epsilon, yi plus epsilon. Hence, as this interval is an interval of length 2 epsilon, the distance between these 2 points will be less than epsilon. Hence, its square will be less than epsilon square, and therefore we have d of x bar z bar is less than d of x bar y bar plus square root of epsilon square plus epsilon square plus etc plus epsilon square n times. Since we can replace each of these quantities yi minus zi whole square for each I varying from 1 to n by this epsilon square. We can write epsilon square instead of each of these quantities. So we will get square root of epsilon square plus etc plus epsilon square. The sum contains epsilon square n times. That is, we have obtained the inequality d of x bar z bar is less than d of x bar y bar plus square root of n epsilon square, n times epsilon square. Also, we know that epsilon is less than r minus d of x bar y bar divided by root of n. So, root of n into epsilon will be less than r minus d of x bar y bar. Here, this root of n into epsilon is equal to this quantity. So, we can replace this quantity root of nx epsilon square by this number r minus d of x bar y bar by applying this inequality. So, we have d of x bar z bar is less than d of x bar y bar plus r minus d of x bar y bar. So, we have obtained the relation d of x bar z bar is less than r. Hence, we have obtained z bar is a member of the open ball centered at x bar with radius r. Since this z bar was an arbitrary point of the set gy bar, we can conclude that gy bar is a subset of the open ball Bx bar R as required, and this implies that tau 2 is a subset of tau 1. Thus, we have proved inclusion in one way. For the other way inclusion, that is to prove that tau 1 is a subset of tau 2, let G be a member of tau 1. We need to show that this G belongs to tau 2 also. To prove this, we proceed from the definition of metric topology. Let x bar be an element of the set G. We need to show that There exists an open ball centered at this point x bar, and that open ball is contained in G. That is, we have to find some r greater than 0 such that Bx bar r is contained in this G. Now, since G element of tau 1, where tau 1 is the product topology on Rn, and since the family of all open boxes is a base for tau 1, we can apply the characterization of bases here. Since x bar belongs to G and G element of tau 1, and since we have a base for tau 1, we can find a member of this base such that this point x bar is contained in that member, and that member is contained in this open set G. So there exists an open box, say W, which is equal to W1 cross W2 cross etc. cross Wn, containing our point x bar such that this open box, that is the member of our base, must be contained in G. Here, this set W1 cross W2 cross etc. cross Wn is an open box, which means that each of these sets W1, W2 etc. Wn are open in the respective spaces. Hence, W1, W2 etc. Wn are here open in R with respect to the usual topology. On R, they will be open. And each of these sets Wi will contain xi, since x bar belongs to W, and we know that this point x bar is an n-tuple of the form x1, x2 etc. xn. Hence, since W is equal to W1 cross W2 cross etc. cross Wn, the first coordinate x1 will belong to W1, second coordinate x2 will belong to W2, and so on. Xn will be a member of Wn. Hence, we can say that each Wi will contain xi. Here we have the point xi belongs to Wi, where Wi is open in R with respect to the usual topology, and we know that with respect to usual topology on R, the collection of all open intervals is a base for the usual topology. Hence, using the characterization of bases, we can say that as xi belongs to Wi, we can find an interval, an open interval such that xi will belong to that open interval, and that open interval will be contained in Wi. Such an open interval will definitely exist. That is, we can find a real number Ri greater than 0, so that the open interval xi minus Ri, xi plus Ri is contained in Wi. Thus, for each I varying from 1 to n, we will get a real number Ri. So, we will have n real numbers R1, R2 and so on Rn. Now, let 0 less than R less than the minimum of these real numbers R1, R2 etc. Rn. Since each of these Ri's are greater than 0, the minimum of these n positive real numbers will be definitely greater than 0, will be strictly greater than 0. So, we will be able to find an R which lies in between these two numbers 0 and the minimum. Then note that this R is greater than 0. R is definitely positive. Also, z bar element of b x bar r will imply that d of x bar z bar less than r. So we have considered an open ball centered at x bar and with radius r, and we are trying to prove that this open ball is contained in G. Applying the formula for Euclidean metric, we can write d of x bar z bar as summation over I varying from 1 to n xi minus zi whole square, and that is less than r, which implies that summation I varying from 1 to n xi minus zi whole square is less than r square. Since we have considered only the squares of the differences xi minus zi in this sum, and we have obtained that this sum is definitely less than r square, should imply that the distance xi minus zi must be strictly less than r. Each of these differences should be less than r for each I varying from 1 to n, and we know that this r is less than ri for each I, since r is the minimum of r1, r2, etc. rn. This implies that zi belongs to wi, as zi is a member of the open interval xi minus ri xi plus ri, and that is contained in wi, as we have already assumed. This implies that z belongs to w, as the above statement is true for each I, and this will imply that z belongs to G, since w is contained in G. Thus we have proved that whenever z bar belongs to b x bar r, z bar belongs to G, which implies that b of x bar r is contained in G as desired. Therefore, G belongs to tau 2. Since G is arbitrary, we have showed that tau 1 is a subset of tau 2. These two inequalities, tau 1 subset of tau 2 and tau 2 subset of tau 1, implies that tau 1 is equal to tau 2 as required. Hence, we have proved our claim that Rn with the usual topology coincides with Rn with the product topology. So, the product topology on Rn is equal to the usual topology on Rn as required. This completes our proof.